I'd like to introduce Scott Coulton, who is a solution architect with Health Direct. Please welcome him.
Hi, good morning. Good morning, thanks for coming out and listening to my talk. So Batman today is going to explain why we should containerize our life, or the problems we're going to find once we go to containers. So these are going to go through some of the pitfalls we found and then go through the solutions. I've tried to be very vendor agnostic and showed multiple solutions depending on the issues you have. So in your solutions in your infrastructure, you can make the right choice and get the right tool for the right job. So here's the agenda. So first of all, we decided to use containers. We're going to go down that road. Then we're going to look at the pitfalls of using the containers. And then we have a solution to that problem. And then is it ready for production use? So this is a quote I really like. It's, have you ever danced with the devil in the pale moonlight? And the devil does not change, he changes you. And that's quote the Joker from the Batman movie in 1989. And this quote is really relevant when starting out with containers. If you think that you can have the same development practices and the same processes and just put containers in, you are completely wrong. It will not work for you and you'll go, I hate containers, I never want to do this again. We already heard this morning about how process and culture is more important than technology. And that's why I like this quote, because you have to change your culture to adapt with the technology so you can be delivering applications quicker to market. The thing is, if you're trying to use containers just to solve technical debt and you're already broke, you're just actually borrowing more money in smaller chunks, making you more broke in little more chunks. But over the end of the day, it's the same technical debt you've got to pay off. So before starting out, you really got to have a look and think about your processes and changes. Because if a developer wants to deploy a container straight away and it's going to take him 2 days to go through an infrastructure team, there's no real point of doing it, because we could have done a VM in the same time. So let's have a look at, say we've decided to start using containers. So as you've already heard this morning, there's a lot of buzz around containers. Why should we use containers? Is this the next big thing? So we'll have a look at this from 3 different points of view. We'll have a look from the developer's point of view, the infrastructure point of view, and last of all, the business. So if you're in the architecture space or you're trying to sell a solution, it's always the business that needs to sign off on it. And if you're going to change drastically the processes on how you're going to deliver applications within the business, they want to know why they're spending that money and the benefits they're going to get out of it. So why do devs like containers? Devs love it because it's quick build times. They can run Docker on their local machine. They can run the same code, the same Docker file on the local machine as they are going to do in production. So minus some parameters or secrets, it is exactly the same code. So you have to, excuse me, I've got a touch of the flu and my throat's super sore. You've got more efficient test cycles. So the dev can actually spin it up, build it, test it, and deploy it all on his local machine, and it replicates what it does in production, making your test loop minutes, not days. So if a dev before was waiting for a virtual machine for 2 days or an instance for 2 days, they can now replicate the same thing in Docker on the local machine in minutes and get the dev cycle and get the loop and get the unit test cycle back to say, hey, this is wrong, or we need to do this, or how can we fix this problem. So the dev loop is now really quick. So developers are going to be quicker to market with their features, but then infrastructure's got to keep up with that, right? So it also makes the CD/CI process fairly simple, because now you've got a standardized build for application development and infrastructure rolling out on top of the abstracted layer of the operating system. So what about the infra guys and girls? The application is now abstract from the host operating system. So if you're in infrastructure, that is really good, because there's no, it's the pets and cattle, right? You don't actually care about the underlying OS anymore. You only care about the container and the Docker engine itself, or if you're using Rocket or Atom. In true DevOps, it's infrastructure as code now. So one thing that we noticed is, as an infrastructure team, we had to become a development team. So the team I actually head up now is called the platform team. We used to be infra, and we actually do platform automation development. So we're an actual development team that has sprints, uses agile, and builds out pipelines for application developers to be able to take advantage of to roll out their application code. So that was the biggest cultural change. We had to go, hey, we no longer look after boxes and cables. We actually write applications to enable the application developers to deploy their code. So if you look at the old process of logging into servers and doing anything like that, we don't do that anymore. It's 100% hands off. Everything's in code and everything's automated. Everything goes through a build process and everything's unit test. As an infrastructure team, that's quite a flip on the head compared to the old way of doing things. But as I said before, it needs to be done to make the technology work, but also make the business work and get the business value out of what you need to do. As you can see here, I say it creates a collaborative environment, because no longer, if your infrastructure team's a dev team and your dev team's a dev team, now we're kind of talking the same language. Even though they might be writing applications in Java, and like my team, we use Golang and Ruby. The CD process, the unit test framework, the applications we use are all bolted together. So now we're talking apples and apples, not apples and bananas anymore. And as I said, it makes the CD process easier, because if you've moved to infrastructure as a code, obviously you want unit tests around that sort of stuff. Bringing Docker into that same pipeline, it makes it quite easy, and it can bolt into your application CD/CI process. And now the business. So if you're going to go to containers, the first thing you're going to do is you're going to say, okay, I need to do all this change up front. I need to have a look at how I'm going to do CD/CI. I'm going to have to do this. And the business might say, well, we've just paid all this X amount of dollars to put CD/CI in. Why would we want to go change that now because of containers? Well, as I said before, collaboration breeds efficiency. And if a project is over budget because it's running behind because of two teams not being collaborative, working towards this can actually bring the cost of the project overall down, which the business loves. And because you're releasing more frequently, you're having increased quality of releases for a few different reasons. One is because the developers can have a quick dev loop, so they can fix any bugs quicker. The QA team can spin up a whole application and test it on every feature branch, or multiple versions of the same application and feature branches in containers. The containers are platform agnostic, so it doesn't matter what platform you're using, and they're language agnostic. As I said before, we write our apps to help developers in Golang or Ruby. All our other apps are Java apps, and even some of the front-end guys, there's the battle at the moment between Node.js and Phantom.js. I'm not a front-end guy, I don't really get it. But some of them use Phantom.js in their containers, and the other front-end guys use Node.js. The QA team doesn't matter, they just point their test at it. And that sort of abstraction, and to build that into a VM before wasn't so easy. And then you're starting to go down the pets road where you actually care, because you've got this version here and things like that. Docker abstracts that, or containers abstract that, and it makes it really easy for devs to be able to try out new things. So you could have them have a version of Node.js that they want to try, and they can actually dev that locally, make sure it works, without putting an infrastructure request in to say, hey, I need a new server, I need this version of Node.js, I need and then they go, okay, infrastructure, this will be 2 weeks and stuff. They can actually take the initiative themselves. They can get build a Docker file with the container of the application version that they need, and they can do all that end to end without even putting an infrastructure request in. Again, it gives devs back more time and more responsibility to get what they need to deliver the application for the business quicker, which inevitably will save the business money. So where do we start? One of the things with the new technology is you've got to gain trust. If the business doesn't trust it and you try to roll it out, and it fails, it's tarnished usually for a long time. And I know from the solution space, if you're going to roll something out and it's as drastic as you've never used containers before to go into containers, you want to have a sweet taste in the mouth to the business, because every time you bring up a solution again, if the first one failed, they're always going to go, oh, what have we done different? Why did it fail last time? Blah, so on and so on. So pick something small. Pick a service that you know. Pick a service that devs are familiar with, and make sure it works first. So I've seen other people I know go, oh, I containerized this and the service didn't work properly, but that wasn't the container's fault. There was issues with the service before they containerized it. So make sure when you pick a service that you know exactly what is happening. It's not something that's been sitting there for ages that someone goes, oh yeah, a guy built that 2 years ago and we haven't done a release on it, so that makes a perfect candidate, because we don't really know what's happening with it. And if someone looks at it and we try to migrate that code, maybe it'll get better. Don't do that. Get something that you know that's rock solid, something that your devs work on every day, but something that isn't going to be a major release that could break everything, if that makes sense. I'm sure you all know a kind of service I'm talking about. And gain business trust. So once you've got the business trust, it's easier to roll out containers further because they see the benefit in it. So that always makes it easier. So now you've decided to use containers, here's some of the pitfalls. Now you've got your service up and running, how do you scale your containers for compute resources? How does your infrastructure work out the application code and how much it's going to use compared to, say, the developers are using on their local machines? Where does our data or state reside? So containers and stateless services are like a match made in heaven, but not every application can be stateless. So if you want to move an application that has state to a container, how do we do that? How do we handle failures as well? What happens if the container fails but the OS doesn't? How do we recover from that in a production service? And how do I structure my data now to take advantage of containers? Because that is a problem within itself. So if we run one container on one compute resource, what was the point, really? Like, we're not really saving money or efficiency. So we need a solution to scale. And that word, you really need to define in your business what that means to you, because it can be a very grey area that a project manager thinks that scale means I can do this 100 times and on the same compute resources, and it'll be in 3 AZs, and I'll have HA forever. So just make sure when you are talking about the scale of the container and how they work, define that term scale up front in your planning meetings and your solution meetings. Because are we talking about scale on the same compute resource, which we can do? Does that mean across data centers, which we can do? Or area zones within the same data centers? And what about even application routing within the same compute resource? So if we've got 2 containers running that can't talk to each other because of security compliance, how do we route that application between on the same EC2 instance or VM? So also, containers and stateless services, as I said, are a match in heaven. Unfortunately, not all applications can be stateless. How do we handle this? Should the data live inside the container? Which probably isn't a good idea, because when you upgrade it, you just lost all your data. So maybe not the best way, but you can do it. Maybe map a drive to the compute resource, but then you're tying your container to that compute resource. So you've just coupled it. So if that node fails, then the data's there and it's not going to be able to move to another healthy node if you've got HA set up. Can we split the compute resources from the state? And we'll have a look at this in how we do it in the solution section. And what happens to application failure within a container? How can we design for failure? What measures can we put in place to prevent failure? And how can we auto-heal containers? Because if you look at your traditional infrastructure monitoring and you're looking at CPU resources and just a traditional like Nagios and how that looks at a instance, most of the failures that happen within a container won't be picked up from that. So your node may look completely healthy to the operations team, but the service isn't actually running. So you have to have specific monitoring in place for the namespace and the kernel and some things like that. And how do I structure my data? There are so many moving parts to building an image, creating the container, and the release process. What configuration lives where? So what's the difference between building an image and runtime configuration of the container? How can I test my container that it's running? So if I put this into an automated CD process, how do I know that that image that I've created builds the container and it's working exactly how I need it to? And also, one of the most important things is how does your source control actually look? So where does that live in source control? Does the infrastructure team now own the Docker file, or should that live with the application code? All these will be issues that you'll come up against, and there's probably no right way or wrong way, but we'll go through a few different solutions. So we have a solution to this problem, as you see Batman saying, "Bye, Joker." So how we can scale. Let's define scale on the same compute resource. So Docker's got a product called Docker Compose. That allows you to use the Docker API and push a YAML file that's configurable to scale a container up to a certain amount of times on a same compute resource. Now, if you're using something as like a key value backend for your container environment, like etcd or console, you can actually write some really smart checks and balances about querying the engine API and checking for failures and checking for CPU and being able to scale on the fly. So that's one of the things I would recommend for having a look at the same compute resource. In the more complex world of scaling across multiple compute nodes or AZs, we'd look at container schedulers, as we've heard about today. So Docker's got Docker Swarm, Google's got Kubernetes, there's Mesos, and HashiCorp's got one called Nomad. On another good note, a lot of times I've heard, okay, we've gone to Docker, we don't need configuration management anymore. Let me tell you now, setting up one of these applications is not trivial. And if you're going to manually do that, it's not going to end well for you, because you want these to be all these schedulers to be in a defined state. So when you hit the APIs, there's no difference between any of the different environments you have. So configuration management is your best friend to do this at scale. So I am a Puppet guy, but you can do this with Chef or Ansible or anything else. But we have modules to build any of these because, as I said, you want this to be repeatable. You want to make sure it's in the same defined state, and you want to do it at scale. So that did help us a lot. So if we have a look at our data or our state now, we have actually have two options depending on where we go. So if we've chosen Kubernetes, Kubernetes natively speaks to either the Cinder backend, AWS, GCE, out of the box. So you can actually split the storage of the container to the compute resource. What this allows is if the host fails, the storage resource is actually still available. When the container comes up as a replicated pod, it will come on top. So you actually have never lost your state. You're actually splitting the two up. If you go down to Docker Swarm or Docker UCP module, there's an application for from Cluster HQ called Flocker. And again, it does the same thing. It's a Python application that sits underneath the Docker engine. And it talks to a service that then is the intermediate between either Cinder, GCE, or AWS. And it does the same thing and migrates the code around the ABS backends or the storage around. So what actually happens in the Docker world is when you run Flocker again, you run Docker on top of Flocker. If that node fails, it's a tongue twister, that one. If that node fails and it comes up again on Docker Swarm on the next one, Docker Swarm will then invoke running that container again. And in the volume section, it will speak back to the Flocker API and it knows how to map that EBS volume or the Cinder volume or the GCE volume back to that Docker container. Again, making your state available in case of failure. So I think this is a fairly important one. We spent a lot of time on this, trying to find the right solution, because it is a problem when first going to containers, and it's something that you really do need to sort, because in the perfect world, you have microservices and everything stateless, and you have maybe a Redis cache or something, but it's not always the way. It's not always going to be that easy. So this is one of the things that we picked up that we needed to sort out fairly early on, to be able to give the option to other application developers or other solution architects to be able to give states to their applications if need be. And this is how we protect ourselves from failure. Service discovery is the backbone of our container schedulers. So service discovery will dynamically update the locations of your containers as they move between compute nodes. So what this actually does is you've got two different ways of doing this. So if you're in the Kubernetes world, you've got etcd, and that bolts into SkyDNS. So what that means is if a container fails, and it then moves to another Kubernetes node, the Kubernetes API will actually talk to etcd, which is the key value store in the backend. That will then register the container on the new node. That will then update SkyDNS. And as long as all your other external services are talking to SkyDNS, it will then be able to find the container application, even though it's automatically moved and there's been no change need to be made externally of the cluster. Again, if you use Docker Swarm, you can choose to use etcd, or you can choose to use console. Console actually has built-in DNS, so you can actually, on the compute node, install console, install bind, or DNS mark, depending on what OS you got, and then point it at itself, and the console agent will then speak to the console cluster. And if you ping anything that is your service name service name.service.console, it'll be externally available as long as the DNS on the other services are also pointing at the console cluster. So this gives you a really, really good way to fix up or make everything dynamic. And this is another thing that we spend a lot of time on, because you really want to get this right. You really want to be able to have automatic failure with automatic recovery, because without that, why move to containers if there's a chance that you can't recover as well as you could have if it was a VM? And this is the interesting part that you'll find as you start to move into the world of containers and you start to do more complex applications with dependencies and different secrets across different environments. Base configurations for the container should live in the Docker file. Arguments for runtime should be parameterized in the Docker file, but extracted to runtime configuration. So when the container comes up, it should live in its own Git repo, but it can, when I say its own Git repo could be within an application Git repo as well. What I mean is, do not put like 1,000 Docker files in one Git repo. Bad idea. Because when you make a change to a Docker file and you change it in, your CD process should go, hey, that Docker file's been changed, and then go through and build it. If there's 1,000 of them in the same Git repo, I mean, you can write code to do that, but you've just really shot yourself in the foot and writing code for no reason, because if you had to put it in a separate Git repo, you wouldn't have to write all that code and it wouldn't have to be as complex. Runtime configuration. So that's, should you be using state or stateless container? Should we put memory constraints on the box? So a lot of stuff that we do, especially middleware, is Java. So in the containers, if you just let the Java heap size run wild, it will run wild, and it will smash the underlying host. And if you've got multiple containers running, you don't want that. So memory constraints is something that's good to match up with your Java args in the application and tie them to the container as well, just to make sure. And runtime arguments can be anything like passwords, secrets. Even if you use something like Vault, we use HashiCorp's Vault. At time of build, it will actually query the Vault API and get the secret back dynamically, so we don't have any secrets in source control. That does take some time to set up, but it's worth it if you don't want to put secrets in source control. And the name of the container, that is very important. And I know this is going to sound weird, but you have to define your service somewhere. And whether it be SkyDNS or console, the name of the container is what the service is known as. So whether you're using SkyDNS and you set up whatever service whatever your company domain is, or you're using console, the name of the container is the service. The service is the state of the container, and that's how everything else can find it. So when you are naming containers, you might want to give them names that make sense, not like Fuzzy Cat 1 and that people won't understand. Another thing that some of the dev teams did was just using the name of the service as Docker natively gives it if you don't name it, and that makes it really difficult as well, because every time the container respawns, it gets a new name. And if you've got connection strings or something going somewhere else, and that container name's now changed, when it's come up and it's registered as a new DNS, your whole application's not working anymore. CI/CD. You can write unit tests in any language for Docker. So as long as you can build the container, you can then write your unit tests. We write it in Golang, but you don't have to write it in that. I've seen it done in Ruby and Python as well. But the unit test should live with the Docker file. So no matter where the Docker file lives, whether it be in its own repo and you just want Docker files in there, or if it's the Docker file for the application, it's the Docker file within the application code, the unit test for the Docker file should live there as well. So as part of the CD/CI process, as easy as have the input-output hooks of managing the unit test, making sure the image is doing what you want, because the last thing you want to do is push out a bad image, because that'll break everything. So you want to put some sort of structure around that. So again, like any application code, there should be a hook, an input, and an output that you're expecting from your CD process. Another thing that we've just implemented at the moment is security scanning on the fly for security vulnerabilities of inside the Docker container. So as part of the CD process, we have an application from CoreOS called Claire. When the container is actually built as part of the CD/CI process, we then scan it. And if there's any vulnerabilities, on package vulnerabilities, the build will break and a Slack message will go out and say, hey, whoever done the git commit, that's broken, you need to update the package to make sure that the security vulnerability is gone. So is this ready for production? I'll just quickly go through. This is what, if we tie everything together, this is what Kubernetes looks like. As you can see there's just a couple pods. I'm actually running out of time, so I'll go through this pretty quickly. My slides will be online if you want to check this out later. But this is the application design for Flocker. So as you can see, it's externalized the storage to the compute resource. This is what it looks like for Mesos, if you want to use Mesos. And now, quickly, if I've got any questions.
Any questions? Is anyone watching?
Pardon? Encryption inside containers? I haven't used it. I haven't need to. The only encryption that we use, will encrypt the underlying OS, and then the container will sit on top of that. So the host image is encrypted, but we don't encrypt inside the namespace.
I'm just going to set up the next laptop.
Okay.
If you've got any other questions, you can take them.
Yeah, any questions? Well, no. All right, well, thank you for your time and thank you for listening.